New pictures obtained by the James Webb Space Telescope have dazed analysts. Instead of reinforcing our impression of the universe, these pictures have uncovered an upsetting reality. Our current understanding is insufficient to make sense of the universe's early stages. The theory regarding the universe's beginning reaches its limits, forcing us to consider new ideas about its origins. The inquiry emerges. How was the universe formed, and why does this new discovery challenge even the most experienced space experts? To understand more about the Big Bang and the ever-advancing details of this discovery, we must re-evaluate the possibility of the Big Bang itself. Contrary to popular belief, the Big Bang was not an explosion in pre-existing space. Rather, it was space itself that began expanding around 13.8 billion years ago, along with matter and time. A singularity, a concept in physics and cosmology, describes a point where gravity is so intense that space-time becomes infinitely curved. Today, after billions of years, we observe that our cosmic home is part of a vast and intricate system. For researchers, this represents a crucial aspect of the universe since its very existence and ongoing expansion are key to understanding its nature. The universe is not expanding into pre-existing space. Instead, space itself is continuously growing. According to conventional theories, the first stars began to shine between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Age. This was the era when the first bright celestial objects clustered together to form mature galaxies. However, how quickly these galaxies formed remains an ongoing mystery. A major breakthrough came with the first images captured by the James Webb Space Telescope in July 2022. Scientists reported that the telescope had identified various galaxies, some of which existed around 300 million years after the universe's formation. Compared to cosmic structures that formed billions of years later, these early galaxies were significantly smaller and less massive. This observation aligns well with the established scientific model. The density of matter in the early universe was not sufficient to produce galaxies as large as those observed today. The discovery of 6 unexpectedly bright, redshifted objects by the James Webb Telescope has triggered one of the most significant crises in modern astrophysics. Although these newly discovered galaxies are similar in age to previously recorded ones, they are nearly as massive as our own Milky Way galaxy. This has created a captivating mystery in cosmic cosmology. After analyzing a series of images captured by the telescope's near-infrared camera, scientists identified these light sources. Redshift specialists confirmed that the light from these objects took more than 1 billion years to reach Earth, meaning they existed between 570 and 700 million years after the Big Bang. By examining their properties, researchers concluded that the Webb telescope had captured images of 6 early galaxies. Surprisingly, these galaxies were so massive that they defied conventional cosmological assumptions. Instead of the expected dwarf galaxies, researchers found structures nearly as large as the Milky Way, despite having formed in the universe's infancy. If we continue analyzing the data gathered by the James Webb Space Telescope, we see that this gravitationally bound collection of stars already contained over 10 billion solar masses at that time, with one galaxy potentially reaching an extraordinary 100 billion solar masses. Even with this consideration, the mystery remains unsolved. If these findings are correct, the early universe must have contained significantly more mass than previously estimated. This presents a major puzzle. The identified objects challenge nearly all conventional cosmological theories. Even if just one of these galaxies proves to be real, it would force scientists to rethink past assumptions. Additionally, the density of matter in the early universe would need to be several times greater than currently accepted to explain this phenomenon. Another, equally intriguing explanation suggests that these galaxies formed in a manner completely unknown to us. These discoveries and the debates they spark will lead to further scrutiny of our existing cosmological theories. Many scientists with alternative perspectives express their concerns in academic journals, but their viewpoints are often dismissed. Even those who defend the Big Bang theory continuously face unanswered questions. These questions include fundamental issues such as, why and how did something emerge from nothing 13.8 billion years ago? Can something truly come from nothing, or was there an external trigger? Or was it all a coincidence? Stephen Hawking pointed out that time, as we understand it, began with the Big Bang. Therefore, this process could not have been triggered by something external. Another unresolved question relates to the uniformity of radiation and matter density throughout the universe. No matter which direction or distance we examine, we find similar densities and distributions of galaxies, nebulae, and radiation. Modern scientists explain this phenomenon through the theory of cosmic inflation. However, some extend this idea further with the hypothesis of chaotic inflation. According to this theory, inflation has only ended in certain regions, like isolated bubbles, while continuing indefinitely elsewhere. This suggests that multiple universes could exist, each with its own unique physical laws. This raises a profound question. What if our universe is not the entirety of existence? What if another universe existed before ours? In this scenario, the Big Bang would be part of a larger cycle. According to this perspective, our universe might be part of a grander, more complex structure, possibly engaged in an eternal cycle of collapse and rebirth. However, this is not the only viewpoint in cosmology. Apart from the Big Bang theory, in 1955, an article published by NASA suggested that there may never have been a Big Bang at all. Instead, it proposed that the universe has existed eternally, without a beginning. In this view, the universe's expansion is an illusion, and the continuous formation of matter creates the appearance of constant development. This alternative theory, known as the steady-state theory, suggests that while the universe appears to be expanding, new matter is continuously created to maintain a constant density. Proponents of this theory argue that the universe has no true beginning or end, challenging the widely accepted Big Bang model. However, discoveries such as cosmic microwave background radiation and the redshift of distant galaxies strongly support the Big Bang theory, making the steady-state theory a minority perspective in modern cosmology. The expanding debate, multiverse and beyond. The questions raised by these new discoveries push us toward even more radical ideas, including the possibility of a multiverse. If inflation continues indefinitely in certain regions, it suggests that new universes may be forming all the time. This eternal inflation model implies that our universe is just one of countless others, each potentially governed by different physical laws. Some scientists propose that these universes could interact in ways we have yet to understand, possibly influencing each other through gravitational forces or even brief collisions. This leads to another profound question. Could evidence of other universes be hidden within the cosmic microwave background radiation? Researchers continue to search for anomalies that might hint at interactions between our universe and others. Challenging the foundations of cosmology. The discoveries made by the James Webb Space Telescope have reignited debates that challenge the fundamental assumptions of modern cosmology. If galaxies in the early universe were much larger than expected, this could indicate a flaw in our understanding of dark matter and galaxy formation. Current models suggest that galaxies formed gradually over billions of years, but these findings suggest a much faster formation process. If true, this could mean 1. Dark matter behaves differently than we think, possibly influencing galaxy formation in unexpected ways. 2. The laws of physics were different in the early universe, hinting at unknown forces or interactions. 3. Our timeline of the universe's evolution needs to be revised, with early galaxies forming much sooner than previously believed. What comes next? The scientific community is now facing a crossroads. Do we adjust our current models to fit these new observations, or do we consider entirely new theories about the universe's origin and evolution? The James Webb Space Telescope is still in its early years of operation, and as it continues to gather data, we may uncover even more surprises. Upcoming missions, such as the Nancy Grace Roman Space Telescope and improvements in gravitational wave detection, could provide additional insights into the early universe. If more evidence emerges supporting these unexpected findings, the foundations of astrophysics may need to be rewritten. A new era of cosmic exploration. Regardless of the outcome, one thing is certain. We are witnessing a transformation in our understanding of the cosmos. From the mysteries of the first galaxies to the possibility of a multiverse, humanity stands at the edge of one of the greatest scientific revolutions in history. The universe is far more complex than we ever imagined, and with each discovery, we come closer to unraveling its deepest secrets. As we continue to push the boundaries of knowledge, the ultimate question remains. Will we ever truly understand the origins of the universe, or will the cosmos always hold mysteries beyond our reach? Another fascinating but dubious hypothesis comes from the area of quantum physics and string theory. Some tests have suggested that our universe, and everything in it, might be a projection or a higher dimensional simulation. While this might seem like the plot of a strange science fiction movie, it could be connected to the Kardashev scale, which measures the advancement of a civilization based on its ability to harness energy. If there were a Type 3 civilization capable of fully utilizing the power of an entire universe, it might have created a perfect simulation. However, determining the reality of such a scenario is a profoundly complex matter. Exploring the depths of cosmology and the origins of our universe leads us into a realm of profound mystery and ongoing scientific inquiry. The new images captured by the James Webb Space Telescope have reignited debates about the very fabric of our reality, challenging established theories and prompting scientists to reconsider key aspects of cosmological understanding. At the core of this inquiry lies the theory of the universe's origin, a foundation of modern cosmology. According to this theory, approximately 13.8 billion years ago, the universe emerged from an extraordinarily dense and hot state, expanding rapidly and resulting in the space-time and matter we know today. This epic event was not merely an explosion within pre-existing space but marked the very beginning of space itself. The concept of a singularity, where gravitational forces are so intense that space-time curvature becomes infinite, supports our understanding of this early cosmic event. Yet, the discovery of early galaxies by the James Webb Telescope challenges our assumptions about how quickly structure formed in the universe's infancy. These galaxies, identified within just a few 100 million years of the Big Bang, appear surprisingly developed and massive compared to current cosmological models. One of the key questions raised by these discoveries is the nature of cosmic inflation. According to the prevailing theory, inflation occurred within fractions of a second after the Big Bang, causing the universe to expand exponentially. This rapid expansion would explain the uniformity of the cosmic microwave background radiation observed across the universe today. However, recent findings suggest challenges to early galaxy formation that may require modifications to inflationary models. The formation of galaxies like those observed by the James Webb Telescope forces cosmologists to reconsider the conditions and processes that governed the universe's early history. These galaxies, already massive and fully formed so soon after the Big Bang, suggest a density of matter that exceeds previous estimates. The mystery deepens when considering how such enormous structures could form and evolve in such a short cosmic time frame. Additionally, the discovery of these early galaxies raises intriguing questions about the nature of dark matter and dark energy, two elusive components that make up most of the universe's mass and energy content. While dark matter is believed to provide the gravitational framework necessary for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In response to these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang perspective. Some theories suggest that our universe is just one of many in a vast multiverse, each with its own unique physical laws and constants. These ideas, emerging from advancements in string theory and quantum cosmology, propose a more complex and interconnected universe than previously imagined. One hypothesis gaining traction is eternal inflation, where universes continuously emerge from a larger inflating space. This theory suggests that our universe could be just one bubble among countless others, each with its own set of physical properties. The challenge lies in finding observable evidence to support such speculative ideas, as they push the limits of empirical validation. Another provocative hypothesis posits that our universe exists within a simulated reality, much like a computer-generated simulation. This concept draws parallels to advancements in artificial intelligence and computational science, where simulations can mimic complex systems with remarkable accuracy. If true, our perception of reality as a distinct physical universe could be fundamentally altered, raising profound philosophical and scientific questions about the nature of existence. Moreover, advancements in observational astronomy continue to unveil the vastness and complexity of the cosmos. Telescopes like the James Webb Space Telescope, with its astonishing sensitivity and resolution, promise to reveal even more secrets of the universe. Future observations might shed light on the earliest moments of the cosmos, offering clues to its ultimate fate and the fundamental principles governing its evolution. Beyond observational astronomy, particle physicists are investigating the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central goal of theoretical physics. Models such as quantum gravity and string theory offer potential frameworks for understanding these crucial interactions at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the nature of time itself remains a subject of intense debate. Quantum theories suggest that time may be emergent or even illusory at the fundamental level. Understanding the nature of time within the context of cosmological models could reshape our comprehension of the universe's origins and evolution. Furthermore, the search for extraterrestrial life continues to captivate the public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable conditions elsewhere in the universe. Future missions, such as the James Webb Space Telescope's examination of exoplanet atmospheres, might provide evidence of biosignatures indicative of life beyond Earth. Likewise, scientific pursuits, social reflections, and philosophical discussions about the universe enhance our understanding of our place within it. Questions about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration drive research and debate across disciplines.